January 1991, Operation Desert Storm. The AH-64 Apache was engineered as the ultimate apex predator of the skies, an aerial tank killer built to halt massive Soviet armored columns. Beneath its chin sat the M230 area weapon system, a mechanical marvel capable of unleashing 625 high-explosive dual-purpose 30mm rounds per minute. It was designed to be a symphony of pure, unstoppable destruction. But during the initial phases of the Gulf War, Apache pilots pulling the trigger were met with a terrifying anomaly. Instead of deafening artillery fire, they heard the grinding shriek of stressed metal, followed by dead silence. A staggering 40% of all Apache gun engagements during Desert Storm resulted in a catastrophic weapon jam. Welcome back to DEFUNCT. Today we are initiating a microscopic mechanical autopsy on the belly of the Apache. The M230 chain gun did not fail because it was manufactured with cheap materials. It did not fail because of poor maintenance. It failed because of a fascinating engineering contradiction. It was built too perfectly. Welcome to the tolerance paradox. To isolate the point of failure, we must first execute a complete material stripping of the chin turret and expose the core mechanics. Most automatic infantry weapons, like the M16 rifle or the M240 machine gun, utilize a gas-operated principle. They siphon expanding, high-pressure explosive gases from the fired cartridge to physically drive a piston backwards, ejecting the spent casing and chambering the next round. However, aviation artillery operates under entirely different combat parameters. If a gas-operated system encounters a dud round, the thermodynamic cycle instantly breaks. The entire weapon stops dead, requiring manual intervention to clear the breach. This is an impossible task for a pilot strapped into a cockpit hovering 1,000 feet above a hostile battlefield. The M230 bypasses this critical vulnerability by relying entirely on external power. At the heart of this system is a 2-horsepower, direct current electric motor. By rendering the outer receiver housing transparent, we can observe the drive mechanism. The electric motor drives a continuous loop of heavy-duty double-row roller chain, geometrically similar to a reinforced motorcycle chain. This double-row roller chain must withstand immense tensile stress, repeatedly accelerating and decelerating the heavy bolt assembly over 10 times per second. Connected directly to this moving chain is the bolt carrier assembly. As the motor spins, the chain travels along its track, physically dragging the massive steel bolt back and forth. It forcefully strips a 30mm round from the feed chute, slams it into the breech, strikes the primer, and mechanically yanks the empty brass casing out. Because it uses constant external torque, a dud round cannot halt the cycle. The motor simply powers through the resistance, ejects the unexploded ordnance, and rams the next live round into the chamber. It was engineered to yield a theoretical reliability rate approaching absolute perfection. But perfection is entirely dependent on environmental variables. To understand why this $130,000 piece of aviation artillery choked in the desert, we must shift our analytical parameters back to the Cold War. The Apache was conceptualized and engineered throughout the 1970s and 1980s with one primary operational theater in mind: the Fulda Gap. This region in Germany is characterized by freezing temperatures, heavy precipitation, and thick, clumping mud. Consequently, weapons engineers designed the M230 to physically block out European sludge and chunky debris. To achieve this, they instituted extremely tight mechanical tolerances throughout the weapon's internal geometry. In mechanical engineering, a tolerance is the mathematically defined allowable limit of variation in a physical dimension. It is the microscopic gap between moving parts. If we perform a cross-section cut right through the receiver, we can measure the clearance between the sliding high carbon steel bolt carrier and the stationary aluminum receiver walls. The gap was machined to be incredibly narrow, measuring in micromillimeters. This ultra-tight clearance functioned as an impenetrable physical firewall. Large cohesive chunks of European mud simply could not penetrate the internal workings of the gun. The tight tolerances acted as a scraper, shearing away external debris before it could enter the action. 1991, the Apache was ripped from its intended European environment and deployed to the Middle East. When the Apache hovers, its massive twin engines and 48-foot main rotor blades generate a localized hurricane. This intense rotor wash violently churns the desert floor, creating a vortex of suspended particulates. The chin-mounted M230 is positioned precisely at the epicenter of this abrasive dust storm, forcefully inhaling the material into its feed chutes and receiver housing. Here, it encountered an enemy the design engineers had never calculated into their structural equations: Iraqi sand. This was not the smooth, water-tumbled sand found on a beach. By zooming in to a molecular level using a macro probe, we can analyze the precise crystalline structure of this desert particulate. Middle Eastern desert dust is primarily composed of angular, razor-sharp shards of silicon dioxide. We must place this material on the Mohs hardness scale to understand the physical threat. Where a diamond ranks as a perfect 10 and talc sits at a fragile 1, silicon dioxide registers a solid 7. It is fundamentally harder than the carbon steel and aluminum alloys used to forge the weapon's internal components. More critically, this silicon dioxide was pulverized by the desert winds into particles as fine as talcum powder. Because the abrasive particles were microscopic in scale, they completely bypassed the tight tolerance firewall of the M230. The fine dust easily slipped right into the micromillimeter gaps between the bolt and the receiver tracks. And once the dust breached the perimeter, the very design philosophy intended to protect the weapon became its executioner. Because the tolerances were engineered so incredibly tight, the microscopic sand had absolutely zero mechanical clearance to escape. The gun had essentially become a sealed vault, trapping millions of indestructible silicon dioxide crystals inside the most critical moving components of the firing mechanism. But the physical presence of the sand was only half of the equation. The fatal blow that ultimately killed the M230 was chemical. Standard military maintenance protocols at the time strictly dictated that the weapon's internal moving components be generously coated with CLP, a military-grade liquid cleaner, lubricant, and preservative. In the freezing, muddy forests of Europe, this highly viscous fluid maintained a microscopic boundary layer that kept the heavy carbon steel parts sliding effortlessly against one another. But in the arid Iraqi desert, applying liquid CLP created a mechanical nightmare. When millions of microscopic razor-sharp particles of silicon dioxide mixed with the wet military lubricant, a catastrophic physical phase change occurred. The mixture instantly ceased to function as a friction-reducing agent. Instead, it transformed into a thick, highly abrasive grinding paste, known in machining as a lapping compound. The M230's internal cavity was now coated in liquid sandpaper. To truly comprehend the violent failure that followed, we must analyze the kinetic physics of the weapon's firing cycle. The frictional force opposing the movement of the heavy bolt carrier can be mathematically modeled using a standard friction equation, where the kinetic friction equals the coefficient of friction multiplied by the normal force pressing the metallic surfaces together. Under normal operating conditions, the liquid CLP kept the coefficient of friction incredibly low. But as the silicon dioxide lapping compound built up inside the micromillimeter gaps, that coefficient skyrocketed. Because the mechanical tolerances were so extraordinarily tight, the opposing metal surfaces were literally trying to crush the indestructible Mohs Level 7 sand particles against each other. This extreme spike in friction generated an immense, almost instantaneous drag torque on the external electric motor. When the Apache pilot squeezed the trigger, the 2-horsepower direct current motor desperately tried to pull the drive chain. The internal stress analysis would show the heavy-duty roller chain practically glowing under the tension, as the steel bolt was cemented in place by the abrasive desert paste. If the electric motor continued to pull against this immovable object, the mechanical stress would result in one of two catastrophic outcomes. Either the reinforced drive chain would violently snap, or the extreme electrical current draw would cause the motor to spontaneously combust. To prevent the $130,000 weapon system from completely destroying itself under tension, aerospace engineers had thoughtfully installed a critical mechanical failsafe, a slip clutch. This clutch was designed to monitor resistance. The moment the drag torque exceeded a predetermined critical threshold, the clutch would intentionally disengage, physically disconnecting the motor's rotational power from the drive sprocket. Therefore, when the grinding paste locked the bolt, the failsafe triggered exactly as designed. The electric motor spun wildly, the slip clutch smoothly disengaged, the heavy drive chain stood completely motionless, and the Apache helicopter was left utterly defenseless in the dark. 40% of all gun engagements ended in this exact, frustrating mechanical silence. In the middle of an active war zone, the United States Army could not simply ship hundreds of attack helicopters back to the manufacturer for a redesign. Maintenance crews and armorers had to adapt immediately, performing radical mechanical surgery right on the flight line, often while engulfed in active sandstorms. The first and most immediate fix was chemical. Army aviation units completely abandoned standard operating procedures. They rigorously stripped every single drop of wet CLP out of the guns, cleaning the internal components down to bare, dry metal. Instead of liquid oil, which aggressively trapped the ambient dust, armorers began treating the weapon with dry lubricants, primarily military-grade molybdenum disulfide or dry graphite powder. These dry lubricants provided a highly slick, lubricious surface for the metal parts to slide against without creating a wet boundary layer. Consequently, the pulverized silicon dioxide dust had nothing to adhere to. The desert sand simply blew right through the mechanism or fell harmlessly out of the bottom of the receiver. However, a chemical substitute was not enough to guarantee combat reliability. The Apache required permanent mechanical surgery to completely solve the tolerance paradox. Engineers had to intentionally make the flawlessly machined gun much sloppier. They initiated a massive field retrofit program to introduce what were designated as sand-clearing slots. Using portable milling equipment, armorers literally cut deep, angled relief grooves directly into the solid steel of the bolt carrier and the aluminum receiver tracks. These cuts were not random. They were mathematically calculated structural escape routes. By aggressively milling out these trenches, they artificially increased the mechanical tolerances of the weapon. Now, when the microscopic Iraqi sand inevitably slipped past the outer defenses, it no longer became trapped in a suffocating micromillimeter gap. As the bolt violently cycled back and forth, the mechanical action physically swept the accumulated sand into these newly milled trenches, efficiently channeling the abrasive debris completely out of the weapon system before it could form a jam. By running the guns entirely dry and intentionally ruining the perfect factory tolerances through mechanical relief cuts, the M230's reliability rates instantly skyrocketed. The lethal, rhythmic roar of the Apache's chin gun returned to the desert battlefield. The widespread jamming of the M230 chain gun during the initial phases of Operation Desert Storm remains one of the most fascinating case studies in the history of modern military engineering. It serves as a stark and costly reminder that absolute perfection is entirely relative to the operating environment. A heavy weapon system engineered flawlessly to dominate the freezing, muddy trenches of the Fulda Gap can be utterly defeated by a microscopic, wind-blown grain of Middle Eastern sand. In the complex world of aerospace and mechanical engineering, fighting the environment is often just as critical as fighting the enemy. Sometimes, the only way to make a sophisticated machine truly unstoppable is to give its moving parts a little room to breathe. Thank you for exploring the precise mechanics of history with us here on DEFUNCT. If you want to see more microscopic teardowns of the world's most lethal machines, do not forget to subscribe and leave a comment below, letting us know which weapon system we should dissect next. Stay analytical, stay curious, and we will see you on the next deep dive.